So good morning, good afternoon, good evening to those who are joining this webinar. It's my pleasure to introduce today Dr. Henry Louie, who is going to give us a webinar on off-grid solar systems. Dr. Louie has a lot of experience, particularly in Zambia in this context. He's also an IEEE distinguished speaker for the Power and Energy Society. So we look forward to his presentation and then follow up with the question and answers. So Henry, it's over to you.
All right, fantastic. All right, well, welcome everyone. I'm Henry Louie, and I'm thrilled to be giving this webinar on the fundamentals of off-grid solar systems. And I'm going to do my best to cover sort of the nuts and bolts of off-grid solar systems. As Dr. Singh mentioned, I have experience in this through my research, but also through a nonprofit organization that I run out of Seattle called Kilowatts for Humanity. If you want to learn more about what we do, you can see our website there at the bottom. Most of my experiences come from work that I've done in Zambia and Kenya and a few other experiences, primarily in sub-Saharan Africa. So the lecture that I'm going to give today is loosely based off some of the content in the textbook that I wrote called Off-Grid Electrical Systems in Developing Countries. And because this is just a 1 hour webinar, I'm really not going to dive that deeply in everything. So if you want to know more information, if you want to work through some example problems and so forth, I encourage you to take a look at my book. Okay, so to get us grounded here, let me just first introduce the topic of energy poverty. If you're on this webinar, you probably have some familiarity with this topic, but it's helpful just to ground us all in the same place here. So an easy definition of energy poverty is it's the lack of access to modern fuels. And this typically arises in terms of how people cook and heat their spaces. And about 2.5 billion people rely on solid fuels. So it's typically biomass, like wood or charcoal or crop residue or animal dung. So quite a large portion of the world are energy impoverished when it comes to how they heat and cook. And then we also look at energy poverty as lack of access to electricity. And there's about 1 billion people that don't have access to electricity. So about 1 in 7 or 1 in 8 people on this planet don't have regular access to electricity. Now, most of these people live in 2 regions, sub-Saharan Africa or South Asia. And sub-Saharan Africa is by far the region with the largest energy poverty problem. So there's about 600 million people in sub-Saharan Africa that lack access to electricity. But we shouldn't forget that even in countries like the United States, there are pockets of people that don't have access to electricity. In the United States, this is primarily in our reservations where they have to rely on off-grid solutions. They're not connected to the grid in any way. So any way you dice it, 1 billion people is a surprising statistic to most. That's a lot of people. We've been providing electricity access for over 100 years, and we still haven't reached 1 in 7 or 1 in 8 people. Now, when we think about providing access to electricity to those who are presently off the grid, I like to think of it more as a continuum of solutions. You have small devices like solar lanterns that are good at replacing kerosene or candles. They might even be powerful enough to recharge a cell phone, but it really doesn't solve all the electricity needs of a household. It's very basic. And moving up this continuum, we have larger systems like solar home systems. These might be large enough to power several lights, and they might even be able to power TVs and fans. Again, it's not replicating the grid, but it is providing now a little bit higher tier electricity access. And then we have things like energy kiosks, where now we're into the kilowatt scale systems, and these might be large enough to power refrigerators, freezers, water pumps, things like that. And then at the higher end, we have mini grids, and these more or less replicate the national grid. And in fact, in some cases, many cases, they actually provide higher reliability than if you're connected to the national grid. When I lived in Zambia, I lived in a city with about 500,000 people in it, and every day we had power outages for 8 hours. So we had 8 hours a day we didn't have access to electricity. And the grids that I had worked on in Zambia, when I would go and visit them, I would tell them that they have far better reliability there than I did in this major city. So mini grids can offer higher reliability than the grid. In almost all cases, however, it's much more expensive to supply electricity with an off-grid system than one that is connected, than somebody who is connected to the centralized grid. And that's just a fact. You don't capture the economies of scale, and most often these off-grid systems aren't subsidized by the government like on-grid customers are. So today we're going to focus more on the larger systems, the energy kiosks through mini-grid systems. So we can take a mini-grid and we can really break it up into 3 subsystems. We have an energy production system, a distribution system, and an in-use system. And what this looks like for each system, for each mini-grid, for each project is going to be a bit different. But today we're really going to focus on parts of that energy production system. The distribution systems for mini-grids look very similar to what you might encounter in Western countries. There's going to be distribution lines, perhaps transformers and other components like that. And the end-use systems are going to be fairly similar. I think the meters are going to be a bit different, but we're going to focus today on parts of the energy production system. So in particular, there are about 5 building blocks that go into off-grid systems. And these can be arranged in different ways depending on really the energy conversion technology and the load. Now, because we're talking about solar systems, I'll show you the most common architecture. The most common architecture looks something like this. You're going to have a PV module or perhaps several modules arranged in an array, and they're going to be connected to one or more charge controllers. The charge controller itself, its main purpose is to make sure that the battery that establishes the DC bus voltage isn't overcharged. So batteries, if you're familiar with them, they're quite expensive. They can be the most expensive component in an off-grid system, and they're very temperamental. And how you charge them and how you discharge them really affects how long they last. And so the charge controller is trying to prevent the battery from failing. It's trying to keep it in service for as long as possible. So it's a critical component in an off-grid system, but it's one that you actually do see systems without that charge controller. These would be more improvised systems that maybe somebody in a rural area cobbles together and they connect their PV module directly to a battery. But in most engineered systems, you do see that charge controller. Now, some charge controllers actually have another feature, which is maximum power point tracking, which I'll talk about a little bit later, but you can think of it as just maximizing the power produced by the PV module or PV array. So the charge controller and battery are coupled together on that DC bus. And that DC bus is going to have a nominal voltage, usually of 12, 24, 48 volts. And in very, very large systems, it'll be higher than that. But it's rare to see anything higher than a 48 volt system if you're talking about a 5 or 10 kilowatt installed capacity. So typically we're in that voltage range. And of course you would want a higher voltage with a higher powered system. It keeps your cables smaller and you'll have fewer batteries in parallel. Now, depending on your load, you may or may not need an inverter. If your system is primarily designed just for lighting, LED lighting, it's possible to serve that directly from the DC bus. But in most systems, and certainly the systems that I work with, the load is going to be AC. And so you need an inverter. So what the inverter does is it converts DC to AC, and it's a power electronics device. And inverters typically will also have a protective feature called a low voltage disconnect. And what that does is it disconnects the load if it senses a battery voltage dropping below a set value. And this is really important if we want to maximize the lifespan of our battery. We don't want to deeply discharge batteries, especially lead acid batteries, because they'll fail a lot sooner. So that's the typical architecture that you'll see. And we're going to go into some of the components in a little more detail. If you want to look at those components, if you want to see what those components look like in a few systems, I've included a couple of pictures on this slide. In the upper right corner is a very, very small system. The charge controller and the inverter, I think this inverter was maybe just a few hundred watts in size. And not shown are the small PV array and batteries, of course, but you can get an idea of the scale. The one on the left, those are the inverters and charge controller for a very, very large mini grid. I think this is, tens of kilowatts in size. So they go from very small to very large, the size of an entire room. Here are some pictures of battery banks. The one on the left, I believe, is something like a 10 or 20 kilowatt hour system, and the one on the right is much, much larger. Those are actually 2-volt cells connected together. It basically fills an entire room. So these are all lead acid batteries that you see there. And of course, much smaller systems, they might just have one battery. So let's talk about PV arrays. And we like PV arrays because they rely on sunlight, which is free, and they produce electricity. They produce DC electricity. So that's nice if we're going to couple it to a battery, that we don't have to have a converter there. It's pure DC. PV prices are dropping, and they're quite low. I think I saw a bid for one of my projects the other day, and it was the PV arrays were about 65 cents a watt, and that was in Zambia. So that's quite low. Now the drawback to PV arrays is that the power that they produce is variable and uncertain, meaning it's going to vary throughout the year, and you're not going to know that far in advance how much energy it's going to produce on a given day. So that means it requires a bit more engineering and a bit more battery backup than if you had an entirely deterministic source. You'll see this is a Radiance Map. You'll see that most of the areas where we struggle with energy access, there's high solar irradiance. So sub-Saharan Africa is that dark orange. That means it's quite sunny there. So most of these rural areas then are going to be good locations for solar panels. Now, more technically, a PV module or PV cell is just a PN junction. So if you are familiar with how diodes work, a PV cell is just a diode. And what happens is when photons from sunlight excite electrons within the PN junction, some of those electrons jump out of the valence band into the conduction band. And if you have a external circuit connected to it, they have a place to go. So a basic ideal model then of a PV cell is shown on the right. It's simply a current source which replicates the photon excited electrons in anti-parallel with the diode, and then we would connect the rest of the circuit to the right. So that's what it looks like. And one of the things that we can keep in mind then from this model is that we're going to expect some nonlinear behavior because there in fact is a diode there. So if we plot out the voltage versus current characteristic of that circuit, you would see that it follows that green line in the plot on the right. So the current is fairly constant for a wide range of voltages, and then the voltage is fairly constant for a wide range of current. And so what this means is if you were to plot the product of the voltage and current, it would trace out that dashed line, which is shown there. And one thing we need to keep in mind is that this power then has a unique maximum, and that's shown by the red dot. And really what we try to do is we try to expose our PV array to conditions which will make us operate right at that red dot. But there's no guarantee that we're actually going to operate there. We actually need to actively control the PV array to get it to operate there. Now, just as a practical matter, I want to introduce you to PV PV spec sheet. So if you're going to be installing a system, maybe you're on this webinar because you're interested in installing a system, designing a system for a community center or a school or something, you need to become familiar with the spec sheets for the different equipment that you're going to be looking at. So one of the most important things to understand about PV module spec sheets is that the values that you see have all been tested by the manufacturer at a reference condition. And that reference condition is called standard test conditions, or STC. And briefly, that means that they've exposed the solar panel to an irradiance of 1,000 watts per meter squared at a special predefined temperature of 25 degrees Celsius and at a special spectral distribution of irradiance. So they've tested the solar panel under these conditions, and they've taken measurements, and that's what goes on the spec sheet. So you have to ask yourself then, well, how will my solar panel actually perform? This particular panel that I've shown, whose data sheet I've shown here, is the iTech SE350. So it has a rating of 350 watts. But if I were to put that panel in my house here in Seattle, would I expect it to produce 350 watts? Under what conditions would I expect that to happen? And of course, the answer is, well, it will produce 350 watts at most under standard test conditions. And standard test conditions almost never occur in the real world. There's always some deviation with irradiance or temperature. So in Seattle, we're never going to see 1,000 watts per meter squared irradiance in the winter. It just won't happen. We might see 10% of that. So we have to know how to adjust or interpret the PV array rating based upon several factors. And these three factors are the irradiance, the temperature, and what the load is that it's connected to. Again, there's no guarantee that a PV panel is going to operate at its maximum power point. So how we can do this, there's an equation that that's called Osterwald's method that we can use to correct for it. And I'll put it up here again, the book, and I have slides on my website that go into this in a little more detail. But basically, we have a factor where we take the irradiance that we have incident to the panel at any moment. We divide it by 1,000 because that's the irradiance under standard test conditions. So that gives us a linear scaling, and then we also will correct it versus temperature, and that's what the equation, or part of the equation on the right there, shows. So you need to know the power coefficient, which PV manufacturers report, and you can do this then to estimate the power production by your PV panel. Now, if you're interested in the energy that a PV will produce over the course of the day, you need to know something about the irradiance of the location, and you also need to know something about how that PV array is going to be tilted. One way that we measure the solar resource of an area is called insolation, and it's just the integral of the irradiance. And so what you're going to do is you're going to take the irradiance and you integrate it over the period of a day, and you're going to get something called, we call it sun hours, and typically you're going to get a value between, say, 4 and 7. And you just take that value and you multiply it by your PV rating, and that will actually give you the estimated energy production for that day. So a simple way of doing this is you just simply take the rated power of the PV array or module, and you multiply it by the number of sun hours, usually a value between 4 and 7, and that will give you a very dirty estimate of the energy produced. Now on the right there, I've shown you how the tilt might affect the power production over 2 different seasons. And I've shown it when the PV array is flat on the ground, which is the dashed blue line, when it's tilted at latitude, which is shown as the black line, and when tilted at twice the latitude. So you can see that if you tilt your PV array at its latitude, so you just look at the latitude of the location and tilt it at that value, it will provide the most consistent power production throughout the year. It's going to underproduce a little bit in the summer and winter, but it's overall better than keeping it flat or, say, tilting it up at a higher value than its latitude. So that's a good rule of thumb. is to just design your array to be tilted at whatever latitude the installation will be at. So again, that orientation is an important factor. One of the other things that you need to be aware of is shading. And I won't go into this in detail, but you want to avoid even partial shading of your PV module. A PV module can only produce, I mean, a general rule of thumb is, you look at the cell in that module that is the most shaded, and that's going to be the bottleneck. That's going to limit the power production of that entire cell. So you can shade just a small fraction of a PV cell or a PV module, and it will dramatically decrease the power production of that whole module. So you want to avoid locations where it's shady. Here's a picture of a PV array that has shading in the evening time as the sun passes over that big tall tree. Okay. So most often you're going to take several PV modules and you're going to connect them together. And when this happens, we call it an array. Now, when we take different modules and we connect them together in series, we call that a string. And we often will take several strings and connect them in parallel to increase the overall capacity of the PV array. So here's an example of what that might look like here. So this is a 6-module array where we have 3 strings of 2 modules each. And so by connecting it together like this, what we do is we've doubled the output voltage because we have two modules connected in series for each string, and we've tripled the output current because we have 3 strings. So by adding more modules in parallel, you increase the current, and adding more modules per string, you increase the voltage. Now, the great thing about PV modules is if you want to know the power production of an entire array, you simply look at the power production of any one of the modules and you multiply it by the number of modules. So if you have a 300-watt module and you have 10 of them and you connect them in any combination, you would expect it to produce 3 kilowatts. So in general, though, what we try to do is we try to put more in series than in parallel. That's usually will result in a more efficient system if you put more in series than in parallel. Okay, so that's our energy conversion system. That's what provides energy to our off-grid system. We generally want to have batteries. In fact, we need to have batteries in solar-powered off-grid systems to stabilize the DC bus voltage and to allow us to produce power at night. So battery banks are very crucial. Don't overlook the engineering involved in selecting and designing the battery bank. Batteries are expensive, and they are usually the shortest lived component. So we have some systems that we installed 3 to 5 years ago, and those batteries are starting to show signs of that they need to be replaced. So that's about how long, in my experience, these batteries, lead-acid batteries, will typically last. So here's an example on the right of the flow of power into and out of a battery. During the day, the battery is, breathing in, it's getting charged, and then overnight, it's going to be discharging as people like to use electricity at night. So the battery is providing a buffer between when the electricity is produced by the PV module and when it is consumed by the users. And there are several types of batteries that one could choose for an off-grid system. What we see mostly now are lead-acid and lithium-ion batteries, and I'm going to focus more on lead-acid batteries. Again, the book has more details on lithium-ion. But regardless of the type of battery, they all work by basically exploiting some chemical reactions between the electrolyte and the electrode to create a separation of charge. And so whenever we separate charge, we're going to have a voltage associated with it. And the voltage that we measure across the battery, it's important to understand that it's very nonlinear. It depends on the state of the chemicals involved, including their concentrations and the temperature. So batteries are very much nonlinear devices, and we can model it reasonably well with something called the Nernst equation, which I'm not going to get into detail here. But in general, as the batteries charge or discharge, their chemical state changes, and so will their voltage, their open circuit voltage will change as well. So unfortunately, batteries should not be modeled as constant voltage sources. Their voltage varies dramatically, perhaps, as the battery is charged and discharged. Now, it's important to be able to interpret a battery specification sheet. We do this. There's lots of information that the spec sheets provide, and I'm going to pick the three most important pieces of information provided, and that's how to interpret the nominal voltage, the capacity, and the cycle life. So those are the three most important things that you need to understand when trying to interpret a battery spec sheet. So the nominal voltage it's approximately equal to the average voltage of that battery when you do a charge and discharge cycle. So we shouldn't interpret the nominal voltage of a battery as the open circuit voltage. That's not the case at all. So you've heard of probably the most famous battery out there is the 12-volt lead acid battery. Well, a 12-volt lead acid battery, when fully charged, will not have a voltage of 12 volts. And when it's discharged, it will not have a voltage of 12 volts. It'll be much lower. So these are just nominal values. And I think a mistake that a lot of beginners make is assuming that, oh, if I find a battery and its terminal voltage is its nominal voltage, then the battery must be full. And that is absolutely not the case. You need to look at the information provided by the manufacturer to understand one might relate the voltage to the state of charge within the battery. So lead acid batteries typically have nominal voltages in increments of 2 volts because each lead acid cell will produce about 2 volts of voltage there, and so we just put more and more in series to get 2, 6, 12, 24, etc. Lithium ion, it will vary depending on the type of chemistry, and when we have a lead acid battery cell that is full, it's going to have a voltage of approximately 2.1 volts. So if you have a 12-volt battery, that means you're going to have 6 lead volt cells connected in series. So you would actually expect to have about 12.6 volts for an open circuit voltage for a fully charged lead acid battery, and it's going to decrease non-linearly with the state of charge as the state of charge decreases. So the capacity of the battery is extremely important. This is really where most of the design work goes into, is selecting the right battery capacity. And there's a lot of misunderstanding on how to interpret the capacity of a battery. Battery capacity is typically measured in amp hours, but sometimes you'll see it represented as kilowatt hours or approximated in kilowatt hours. And the battery capacity is determined by a manufacturer. And let me just show you how this might be done. So you would take a new battery and you would connect it to a load which will draw a constant current. So in this case, this is a battery we took and we discharged it at 8 amps continuously. And then we just plotted the voltage versus time. And you can see that this battery lasted, close to 400 minutes before we were unable to get 8 amps out of it. So to calculate the actual capacity of the battery, we pick a voltage, a threshold voltage or a cutoff voltage, and we see how long it takes the battery to reach that cutoff voltage. And the reason why we pick a cutoff voltage is, although we could continue to get more current out of the battery voltage has dropped so low that it's probably damaging the battery itself, or whatever is connected to the battery might not be operating properly. So in this case, we picked a standard voltage of 1.75 volts per cell. And so we saw when this battery stopped, or when its terminal voltage dropped below 10.5 volts, because there are 6 cells. And it stopped at about 200 minutes. So then we would conclude that this capacity of this battery is 8 amps times 3.33 hours, or 26.67 amp hours. So that's how we would interpret then the capacity of the battery. The manufacturer would report a value like that, and we'd understand that it means that it can provide 8 amps for 3 1/3 hours. Now, an interesting and maybe frustrating characteristic of batteries is that they are again nonlinear. And if we discharge a battery at, say, a higher rate, and we apply that same cutoff voltage, we're going to see that the capacity changes. So if we double the current cutoff voltage much sooner, and in fact, if we calculate the capacity at a higher current, say 16 amps instead of 8 amps, the capacity drops to 21.33 amps. So as we discharge a battery with higher current, it's going to last shorter and shorter, and its total charge that it provides is going to decrease. So if you want to maximize the energy, the charge that comes out of your battery, you want to discharge it at a low current. So a takeaway from this is that a battery really doesn't have a single capacity. It really depends on the discharge current. And any capacity that you ever see is referenced to a particular discharge current. So in our previous example, there's 2 capacities that we determined based upon the current that we discharged it at. So what you'll see is many manufacturers will tell you the capacity based on an hour rate. And the hour rate is just the number of hours a battery can supply a particular current until that cutoff voltage is obtained. So in our example, we have an hour rate of 3.33 and an hour rate of 1.33 that we determined empirically. And so if you look at a battery spec sheet, then you'll see a table or a chart that tries to provide this information. So this battery shown here is called a 1,124 amp hour battery, but of course that only corresponds to one particular discharge scenario. And by default, hour rates are reported at the 20-hour rate, or the capacity, I should say, is reported in reference to the 20-hour rate. But you can see from this table that if you were to discharge it, if you look at the column on the far right, at any other amount of current, the capacity is going to change. So you need to think about your system. You need to think about how it might be discharged. Is it going to be discharged quickly? Is it going to be discharged slowly? And you can adjust the. You would select then the proper capacity for that battery. So in other words, if you have a 100 amp hour battery, that battery when discharged at 5 amps will last 20 hours before its terminal voltage drops below its cutoff voltage. So if you were to discharge it at 6 amps, for example, it's going to last than 20 hours, and it will provide less than 100 amp hours of charge. So again, it's a bit confusing, but just keep in mind that the higher discharge current, the less capacity you're going to get overall from the battery. And the last thing I want to say about batteries is that we typically talk about the depth of charge or the state of charge of the battery. And here's just a picture on how you might interpret that. So let's say we have a 100 amp hour battery and we've been discharging it at 5 amps. So we've been discharging it at 5 amps for 6 hours, so we've extracted 30 amp hours of charge from it. Well, this battery will still then have 70 amp hours left because it's a 100 amp hour battery. So we would say that we are at a 30% depth of discharge with 70% state of charge remaining. I hope that makes sense. Now, again, we could continue discharging our battery if we wanted to get more than 100 amp hours out of it. But once we do that, we operate there in that gray zone in the picture here. And once we're in that area, we risk damaging the battery. And if we go even further, we can actually get to the point where the battery is completely dead. There's no voltage or very small voltage, and the battery's probably been destroyed or its lifespan shortened. So the last thing I'll talk about with batteries is this idea of its cycle life. So again, batteries are often the first component to fail, and we need to have an understanding of how long a battery might last. And the lifespan of a battery is described by its cycle life, where each cycle usually corresponds to one 24-hour period. So in other words, a day. And battery manufacturers will often provide a curve that's similar to what's shown here, where as you increase the depth of discharge, so as you increase the charge provided by that battery each day, its lifespan will decrease, and it's going to decrease in sort of a nonlinear way. And so we define the end of life when the capacity has eroded to the point where even at full charge, it's only 80% of its new value. So as we cycle the battery, as it ages, its maximum capacity is going to decrease. So what we would do then is we would estimate our depth of discharge on a daily basis, and we would just draw a straight line up to the appropriate curve if it's a gel battery or an AGM, for example. And then we would just see how many cycles that corresponds to. So if we pick the AGM battery, we might get 1,100 or 1,200 cycles. If we pick the gel battery, maybe it would last 2,000 or 2,500. And then that would give us an estimate of how many years we can go before the battery would need to be replaced. So a lower depth of discharge, we get more life out of the battery, but of course you need a larger battery then to operate like that, or a smaller load. Okay, so just briefly then about charge controllers. So what we do with the charge controller is we're trying to prolong the lifespan of the battery, and we do that often by sensing the battery voltage and operating a series like chopper switch to regulate the current into the battery. And smarter charge controllers will use a 3-stage charging process where if you look at the battery voltage begins the charging period at a low state, and we try to charge it as fast as we can up until we reach a particular voltage called the absorption voltage. We hold that voltage constant because we don't want to overvoltage the battery. It again damages the battery, and we charge the remaining 10 or 20% of the battery until it's full, and then we drop it into the float stage where we're just trying to maintain sort of topping off the battery. So we see 3 stages: bulk, absorption, and float. And the current then will vary. As soon as we get to the absorption stage, the current starts to taper off as the state of charge gets closer and closer to the absorption set point. So I'm going to end here with a brief discussion on planning off-grid systems. You can argue that there's about 8 steps to planning an off-grid system, and you would begin by coming up with potential communities to work in, or potential projects. And you might do this by looking at demographic data, or maybe you have an in-country partner and they have a number of sites. You will need to do a site assessment. You'll need to go or send somebody who's knowledgeable to visit the actual sites, to collect data, to talk with the community, to get an understanding of the needs and the potential there. Then you'll make a decision on whether or not to move forward with your project. And this decision the criteria for that decision are going to depend on your organization's goals. So maybe you're trying to earn money on it, or maybe you're trying to impact the most people. But whatever it is, you're going to decide which community to work with, if any. And then you get into the technical and commercial design, where you're going to use one or more design methods to size the system, and you're going to couple that with the commercial aspects, especially if you're trying to make money off the system. But I would strongly encourage you, even if you're not trying to get into this for profit, if you're doing it strictly for charity, to really think about the ongoing costs of it. You are going to need to replace batteries at some point. Things will break and they will fail, and you have to ask yourself, how are we going to recuperate those costs? So you really need to think about that. Then you get into pre-implementation, where you're planning the logistics of the installation, you implement it, and then you have perhaps a long period of ongoing operation before you decide to maybe expand it or retire it. And if you're thinking about in doing an off-grid system, you need to think hard about step 8 there, particularly the retirement part of it. So, the best practice is to save money, put money aside, and have it available then if the system needs to be decommissioned. So the batteries need to be removed, the solar panels and charge controllers need to be removed from site. You don't want to just leave those components out there, especially lead acid batteries. You don't want to just strand those in the community. So that should be given thought at the start of the project. My organization, we include that in all of our grants and proposals. We keep money aside for the decommissioning of the project, which isn't necessarily a bad outcome. You know, in one of our projects, for example, the grid extension finally made it, and so the project was no longer needed. So we're in the process actually of decommissioning it now. When you get into the design, which is really step 4, for solar, you know, you're going to be looking at, you need to know the solar resource, which you can often get that information from satellite data, which is available on the internet, and an idea of the demand. And you put this together into one or more design approaches, and then you get the component ratings. So I'm going to go quickly through this. Again, this is in my book, and I have slides on my website that go into it in more detail. But you need to do a load estimation to understand how large of a system that you want. And there's several different approaches. I'd say one of the most common is the bottom-up approach or the survey approach. In the bottom-up approach, you basically look at all the components, all the appliances, how many, what their rating is, how long they're going to be used, and if they're going to be fully used, and you come up with a daily energy use. And you do that for every component, and then you just simply total it, and that gives you your energy production, or excuse me, your energy demand, and then you would design the system based upon that. A way to help understand what appliances might be used is to do a survey. Usually this is a door-to-door survey where you ask questions like what appliances might you own and how often will you use them. But surveys are very error-prone, and I would say that you should only use them for a general sense of the energy consumption, and you shouldn't hang your hat on the results, so to speak. So it's well known that they're error prone, and don't believe everything that you're told from the surveys. Here's a few tips just to make your system a little more at least financially stable, is to look for industrial or commercial users. They're the ones that are going to have more consistent consumption, and they'll likely be able to pay for their connection. Almost universally, the majority of the consumption is going to be attributed to a small number of users. Most users are going to use 0 or a very, very small amount of energy per month, you know, a few watt hours even. But a few are going to use a lot. And so if you want your system to be financially sustainable, you need to find those users that do consume a lot. Most of the load profiles are going to be such that most of the consumption for households anyways is in the evening, which of course is a problem with solar. It means you need to have a larger battery. There's a lot of day-to-day variability, and although most people report a growth in load over time, it's not universal. Here are just some examples of load profiles that you might see for different types of users. Again, you want to, ideally, if it's a solar system, you want most of the energy to be consumed during the day when the solar is producing, but unfortunately, most households and many businesses consume in the evening when it's dark. I'm not going to get into the details of design, but basically there's 2 approaches. You can design your system based upon standards or rules of thumb, or you can use a computer-aided simulation. If you do a computer-aided simulation, I'll just remind you that, you know, the results of the computer-aided simulation, the computer design, is only as good as your input information. So if you're making wild guesses about the load, about how sunny it is, all of that, then the result that you get from the computer program is going to be off. So basically, I always say garbage in, garbage out. You want to make sure that you have good information going in if you're going to trust what you get out of the system. So one of the most popular tools that's used is a program called Homer, and I encourage you to go check them out if you're looking to do off-grid system design. But again, it's going to give you an idea of how to design your system. And again, if you're just making up or you're making wild guesses as to what your load is or your other inputs, then the outputs of Homer aren't going to be trustworthy. Here's just a list of a number of standards that you can consult to help you design a system if you want to do an intuitive design approach. There's quite a few that are out there. They'll tell you how to size the batteries, the PV array, all of that stuff. So you can consider taking this approach if you don't want to use a computer-aided numerical approach. And I'll also just reiterate that this is going to be an iterative process where you're going to come up with the design, you're going to figure out how much it costs, you're going to hopefully consult with the community to see if the design is something that works for them. And you might have to go back to the drawing board, or you might ultimately decide that it's not feasible. So don't be afraid to walk away from a project if you don't think it's going to be successful. So here's my contact information, and I think I left about 10 minutes for questions, which I'm more than happy to answer. So it's a whirlwind tour, and again, there's more information on my website. If you go to drhenrylouis.com, you'll find more information there. And I'll turn it over to Dr. Singh to ask questions. Thank you so much.
Thank you so much for the very comprehensive description of how to design and the components in a solar electric off-grid system. So I encourage everyone to submit questions. Please type them into the text box. And we have one question from Mario Aleman. So his question is, what are the challenges in the sub-Saharan region in terms of PV module performance, considering factors like environment, dust, and high temperature? Also, what's the long-term durability of these PV modules installed in that area?
Yeah, excellent question, and I think you provided a few answers in your question. So in sub-Saharan Africa, in my experience, dusting is a problem. So if you don't regularly clean your panels, you're going to see a decrease in performance. So there needs to be somebody then who's in charge of that. Usually the high temperature is also a problem. You might lose 15% of your energy production because of the temperature increase associated with high radiance values. There's really not a lot that you can do about that. I mean, you could select panels that have better temperature coefficients, but in general, you might have to make up for it by just increasing the capacity of the system. I'd say that theft is also a worry, and you should have some sort of precaution against the theft of solar panels, making sure that they are mounted in a very secure way, or putting razor wire or barbed wire around the rooftop. I've heard of some reports of not theft, but vandalism, people throwing rocks at the solar panels and all of that. So some level of community engagement, depending on the project, is usually appropriate to try to help people understand that this is why the project is good and beneficial. So hopefully you decrease the likelihood of theft or vandalism. Some of the other issues that you hear of are getting fake or counterfeit or underperforming solar panels. So you definitely want to inspect the solar panels. If you're using an in-country installer like my organization does, you want to make sure that the panels that you got matches what was given to you in the organization's proposal. So due diligence is absolutely needed, and you need to do commissioning too, just to make sure it's performing the way you expect it. I don't know if I answered all parts of that question. Polly, could you remind me if I forgot something?
Yeah, I guess the only other question was long-term durability of these modules in this area.
Oh, yeah. So, the rule of thumb is that a PV panel is going to last 20 to 25 years with an average degradation of about 1% per year. Now, what you need to keep in mind is that 1% per year is usually not a constant rate of degradation. might come in more steeply towards the end of its life or more steeply at the beginning. So I've looked at quite a bit of research on this, and it certainly varies. And it's also something that's really hard to determine in the field because there's a wide variety of environmental factors that could affect PV production. So in other words, 1 year is not, if you see a small decrease from 1 year to the next, you can't necessarily blame that on the PV panels. It could be that year was slightly warmer or slightly less irradiant. So it's really hard to track that from 1 year over the next. It becomes slightly easier if you have like a 20-year record to do, but at that point, you're not really using that information to make any any operational decision. It might just help you understand when to replace them.
Great, thank you. A comment from Rodolfo Lopez. He said, I love the presentation. It was brief and very clear. Another question was from Vito Hamza. If we have 10 batteries in our energy storage system, how should we replace them? Should we replace them all together at the same time, or should we replace them one at a time?
You need to replace them all together. What you want to avoid and what you should never do is to mix old batteries with new batteries. Batteries are going to age at different rates. The risk is that if you mix old batteries and new batteries, that the newer batteries are going to provide, they're going to charge differently, they're going to discharge differently, and you might actually have newer batteries discharging into older batteries. So absolutely, you need to replace them all together. And in fact, when you install batteries, you really want them to be all from the same manufacturer, even the same lot. You want to make them as consistent as possible.
Great, thank you. Please type in additional questions. While I'm waiting for the next question, let me ask you a question then, Henry.
Yeah.
What are some of the common failure modes for PV systems in your experience?
Yeah, I mean, I think most people would agree that the batteries are the weak link. They're the ones that the moment you install them, they start degrading. Especially, I would say that one of the biggest challenges is that in most off-grid systems, we don't install the components, the batteries, the inverter, the charge controller, in temperature-controlled environments. And so most of those components are designed to be installed in temperature-controlled environments because they're designed, for Western countries, for example. And so you see higher failure rates because the temperatures are much higher. Batteries fail much faster at higher temperature. Certain like electrolytic capacitors that you see in inverters fail faster when it's warmer. So battery failure, and battery failure is often not like, it's really more of a degradation of the battery over time. I'm sure people have experienced batteries catastrophically failing, but it seems that the failure is more gradual. In the sites that I've seen, you run into corrosion. You see that on batteries, failure to maintain flooded lead acid batteries, which require water to be added. You see that being avoided. And sometimes it's simple things. We had a system that went out for about a week because the person operating it forgot to turn on a switch to reconnect the system after it recharged. So little things like that can crop up and can be frustrating because it's not a technical failure, it's an operational failure, it's an organizational failure if the person wasn't trained properly or didn't remember how to restart the system. So I think solar panels, not much to worry about there. I haven't heard too many reports of those failing. Maybe they underperform a bit due to dusting or some shading, but solar panels are pretty solid. Hopefully what you do when you install a system, though, is you get a warranty on all your components, at least a 2-year warranty on the power electronics and battery. and hopefully that protects you against some of the earlier failures that might happen. We haven't had anything like that. The only thing we've ever had really is batteries start to degrade faster than we would have expected.
Great, thank you. We have another question from Mercy Chalangat. What's the approximate tariff charge for mini grids in areas where you've worked? In Kenya, they can go up to 4 times what the utility power costs per kilowatt hour.
Yeah, that's a really good question. So there's a couple of factors at play there. One is what the grid charges, what the national grid charges, and that's often not cost reflective, meaning it's subsidized. I would say that most large for-profit mini grids are going to charge anywhere from 50 cents an hour to a few dollars a kilowatt hour, so 50 cents a kilowatt hour on up to a few dollars per kilowatt hour. But that really depends on the operator, and they might have bulk buying discounts where if you prepay for a lot of energy ahead of time, or you're a consistent customer, the rate may go down, and it might be much larger for those people that use just small amounts. I think in most of these systems, the levelized cost of energy, the cost of producing a kilowatt hour, is usually greater than 30 cents, and less than $2. So somewhere in that range is generally what you will need to charge then to at least break even.
Great. Another question from Mario Aleman. In your experience, what's the best approach to recycle PV systems, including lead-acid batteries in underserved areas?
Yeah, this is really, really tricky because in some countries there's not even, there's not a lot of recycling facilities. So in Kenya, for example, I think there's one big one in Nairobi, and if you have lead-acid batteries that are stranded in a rural community, you need to find a way to get them to that recycling center, and which means you should, often involves paying somebody to do it. So what I would recommend is, as you think about doing a project or you're starting a project, to try to identify that end-of-life consideration. Think about where you would be sending these batteries to, and sometimes you'll get paid to recycle the lead once you get them to the recycling center. In one of our systems in Kenya, what we're doing now is there's a local individual who he collects batteries. He'll pay you for them even, and then he'll go and he'll transport them to Nairobi, and he gets paid to recycle them because the recycle center makes, they will repurpose the lead and they make money off it. So in my experience, it's varied widely between having to pay to have them recycled versus paying to have them recycled, or getting paid to have them recycled. With the electronics, it's a similar problem. In fact, that might even be more challenging, where they might not even have centers in that country that recycle electronics. Often, though, the local, people in rural areas will find some use for solar panels if you're decommissioning your system. Larger inverters and things like that, that might be harder to find. It's really a challenge, though. This is an area that we need better solutions in, because there's a lot of e-waste, especially with solar home systems that are going out there. So, I'm actively looking for solutions to this, but it is something that you shouldn't ignore. You should really ask yourself, what are we going to do with these batteries when they fail? Can we send them back to the installer? Can they handle that? And you need to have those conversations, hopefully up front.
Great. We'll take the one last question from Daniel Lotus. So he entitled the single cell bottleneck. In discussing shading, you stated that shading even one cell creates an impact on the entire panel. Is that also true for failure of a single cell? Does the entire panel cease to function?
Yeah, I suppose it would depend a bit on the failure mode that you're talking about. But what we have in a PV module is the cells are almost always connected in series. And so if you have one cell that fails open, for example, then unless that panel has bypass diodes installed, the whole panel then, there'll be an open circuit in that series connection. So it depends a bit on the failure mode. Larger panels are more likely to have some of these bypass diodes where several of the cells could be bypassed if one of them fails. So it depends a little bit on the size of the module or the PV panel that you're talking about. But in general, the cells are series connected. So if there's not way for current to flow through a cell, it's going to dramatically impact the whole module's current or power production.
Okay, well, the time went by so quickly. It was a wonderful, great presentation, Dr. Louis. And thank you for presenting this webinar today. And thank you to all the attendees who attended both the live session as well as the people who watched the archived webinar.